For those who joined us late, this is a question by one of you guys, and we're trying to go through it. So if you're late, we're going to go through this one anyway later on. So let me share my screen. Share. So this is, what problem is this one? This is one of the problem in the review. Is it 81 or?
67 for chapter 26.
67. Okay. So let me draw the circuit. Let me, oh man, did I, okay, I have a pen. Let me draw the circuit. Okay, this is part of this basically review of this question. Okay, so the circuit basically the way that Faraz drew it is that I have a resistor in here. I have another resistor in here. Okay, let me put my screen down. Okay, so I have another resistor in here, and then I have another one in here, and it looks like I have resistors in parallel, but they are not, because now when the switch is closed, I have another resistor in here. Can you give me the value of this one? Was it 6 ohms or 3 ohms?
3 ohms.
Okay, what happened to my pen in here? This was 3, this was 6 then, and this was opposite 3, and this was 6, and what was the middle one for?
3.
3. And we have an EMF in here, a battery basically, that is, how much, 36 volts?
Yes.
36 volts, okay. So, and we're asked to find basically the current somewhere in here, okay? So what we're going to do in this case is, first of all, it has to be in this direction because the voltage in here, this entire voltage and this entire voltage are the same, but I go through, which is 36 volts basically, but I go through only a drop of a smaller height of 3 ohms times whatever current on this side. And the current on this side and the current on the other side, when it was open, they must be the same. But now when it's closed, it may not be the same. But the point being in here is, is that the drop in here is less than the drop on the other side. Therefore, the current must be higher. I mean, the voltage must be higher on this point than the other. So the direction is there. If I don't know what the direction is, just put a sign. And then if the sign turns out to be negative, so be it. It's fine, no problem. So we're going to take in here the current I, the incoming current. We're going to take through this side, I'm going to call it, usually I give it the name depending on the resistors, but it's fine. So we're going to call it I2. On this side is I3. From the get-go, we have I equals to I1 plus I2. I mean I2 plus I3, I'm sorry. Correct? That's the node equation in there. Okay? Yes or no? For us.
Yes, that makes sense.
Okay, so I have another node in here where that I2 will split in such a way part of it will go here, and the other part is the question that we want to know is the current in here, which we're going to call it, we'll have to give it a significant name because we gave I2 on the other side and I3 in there. Okay, I4, so it's fine. I4 and I5, okay? Now when I4 and I5, so that means I2 is equal to, what is it? I4 plus I5. That is the node equation in there. Now, when I3 and I4 meet in here, they must add up to their sum. So this must be I4 plus I3, correct? Through the 3 ohm. And then when they join again, I'm going to end up with I5 plus I3 plus I4. But I3 and I4, what is it? I4 plus I5 is already I3, and I3 plus I2. So basically the last equation, there is no need for it. I'm going to end up with I. Let's check that to see if it makes sense or not, just for verification. We know it's going to be I, but let's check that. So when they join, I have I5 plus I4 plus I3, okay? But I, from the previous equation, I4 plus I5, this is I2. And I2 plus I3 from the previous equation is already I. So that's why we end up with I in here. So there is no need to write a node equation here. So basically what I have out of all of this, I actually have only two equations, because this one I already used it. I already used it when I wrote the current to be I3 plus I4. In other words, I'm trying to minimize the number of unknowns at this point. So I have a bunch of unknowns. I don't know what I is, I don't know what I2 is, I don't know what I3 is, and I don't know what I4 is, and I don't know what I5 is. I have a lot of unknowns in this problem. So let's write this loop now. Let me change the colors now. Let's try this loop now. Okay, for those who just joined us, okay, we didn't really start the class early. We just had a question, so I'm trying to answer it so that we set up the equations for one of the homework problems. But let me set up the equation, then we'll talk about this one, okay? So we have this loop in here. It doesn't matter where I start. I can start for the node, and I can go in the same direction, basically. Okay, why is my screen now? Okay. For some reason, did somebody take control of this or what? What happened in here? Why am I not getting any control over my screen? Okay, so sometimes the mouse is probably not positioned correctly. So the node the loop equation now. The loop equation says that the voltage drop, which is 3 times I2, plus the voltage drop, which is 3 times I4, plus the voltage drop, but I'm going against the current, so it must be minus 6 times I3 is equal to 0. So that's another equation. So 3I2 plus 3I4 minus 6. So it's 3I2 plus, that's a voltage drop, okay, plus 3I4 minus, because I'm going against the current, so I'm rising actually a potential, so it's a negative drop. So it's minus 6I3 is equal to 0. That's another equation. So far we have 5 unknowns, but we only have 3 equations, so we really need more equations to solve this problem. Here is a fourth one for this loop. Again, I drew it counterclockwise, so it doesn't matter where I start. I'm going to start with this node. So the first thing, I'm going to rise in potential because I'm going against the current I4. So it's going to be minus 3I4. Okay. When I go through the 6 ohm, I'm going to go in the positive direction. So it's a 6 in the current, the direction of the current. So it's going to be a real drop. So it's 6I5 plus 6I5. And then I'm going against the current also, so it's a rise actually, which is I4 plus I3 times 3. That is the current in that direction. So it's a minus 3 times I4 plus I5, okay, equals to 0. So that is 4 equations, and remember I have 5 unknowns. So I need another loop, and the other loop could be one of the outer loops. It doesn't matter which. So I'm going to take it in the direction of the voltage, counterclockwise, now following this path, okay? I'm going to go straight from above the battery. So at this point, when I go through, I have a voltage drop of 3 times I2, and I have another voltage drop of 6 times I5, but I have a potential rise of 36 volt. So at the end, I have 3I2 plus 6I5 minus 36 equals to 0. I have enough equations to solve my problems. There are some simplifications probably here when subbing I, this equation gets rid of I completely from everywhere in the problem. Oops, I'm sorry. But notice the other equations don't have I in them at all. They only have I2, I3, and I4. So this equation can be ignored for a moment completely. So I only have 4 equations with 4 unknowns, really. So I could get rid of I2 by using equation 1 and removing I2 from this equation. Wherever I2 appears, there is no other room for it. There is another equation here with I2. So now I will reduce to 3 equations with 3 unknowns. Then use one of the other equations to get rid basically of whatever other unknown. For example, get rid of I3. And then I will end up with the equation. At the end, I do one equation. Okay, let's talk about what we have in business first. And then, does this answer your question for us?
Somewhat, but I'm still like a little bit confused.
Okay. since this is part of the review, we're going to come to it anyway, okay? We're
Okay.
going to discuss this anyway, okay. So we have 9 people today. For some reason, we don't have everybody in here, okay? You know how the plan for the review is. I'm going to split you actually into 3 groups, okay, of 3 people at the same time. And each group will take basically a whole chapter, the entire 5 problems from the chapter. And then you guys go through them, see what kind of a plans on. You already did the homework, so I hope that you know what's going on. And if you have questions like Faraz did, please ask a question so that we can discuss it. And I will come to each and every one of your rooms basically and discuss this problems and see how we can move along. And at the end, when we meet in the lab, basically, we're going to go through each and every one of the other groups, basically, solutions, so that every one of us in here today will have an idea of all of these problems and how to solve them. Does this sound like it's a good plan for our review for the exam?
Yes.
Okay, so where is the group? Breakout rooms. So we'll have 3 groups. Create. You will receive an invitation, okay, from the Canvas to join your own room. All you have to do is click join, and you're gonna leave this room and automatically join that room. When times come when we meet back again together, you're going to be. I'm going to send basically that the rooms are going to break. So it's gonna give you a minute, okay? Basically countdown. So you don't have to leave right away. So you can wrap up, and then we can meet together again, okay? So I'm going to create, so you'll be in 3 to 4 people in a group. You should receive invitations now. Please join them. Hi, Heather. We'll wait for everybody to join us, okay? They should be leaving their rooms now. Okay. Let me share my video. Okay. So I have everybody back in here. Basically, we're going to take a break now because we're meeting at 2:30 anyway for the lab session, which we're going to continue doing this review. So during that time, basically, we go through all of the problems that each group has worked out. And first of all, try to pinpoint some of the interesting things about them and discuss them all. And then we'll leave you on your own for the interview. Please do not forget very, very important things as far as this exam. I'm not going to have a Zoom session basically open because the exam is going to be available actually from tomorrow night until the end of the class on Wednesday. So, but instead, what we have a discussion session basically that I open specifically for this exam. So if there is an issue, for example, with units or something that is not properly probably prefixed, that is not correct or something, it's a good idea to ask it in the discussion session, which means that you guys need to be subscribing to that discussion session to receive any kind of notifications. Make sure that you're aware of it. Short of that, basically what you need to do is check on it regularly. I will not answer anything past 1:30 p.m. on Wednesday because at that point there is not enough time left for anybody to check what's going on. So I'm hoping that everybody would have done their due diligence before that, and you have plenty of time to submit your work. So I'm hoping that nobody would run to that time anyway. Okay, so we will meet in about half an hour, I would say. That's when the lab session meets. Okay, and bring your notes with you guys. Does it sound like it's a good plan? Okay, so I'll see you guys. Okay, so we're back from basically the sessions that we broke in the lecture. Now we're in the lab session, so we're going to go through the problems that we have. Okay, no problem. The predictions turned out to be wrong still, Sebastian, because only a few people showed up. Anyway, the problems that we have are, I think, 15 problems. I know I have most of the classes still not here. And for those who are here, which one do you think we should discuss? I'm leaving it up to you first, okay? And then we'll go systematically. Chapter 26, all of them, or specifically one of them, or all problems from chapter 26? By the way, I mean, if you guys have subscriptions to the online thing, they give you the 14th edition, and that's what I'm using actually right now. I gave up on the book that I have. Okay, so let's look at problems from chapter 26. And they are problems 60, 67, 70, 78, and 81. Okay, let me look at problem 60 first. Oh man, I'm in the wrong chapter or what? So chapter 26. So for chapter 26, basically it gave us, let me first of all share my screen with you guys. Share. So we have two batteries, I'm sorry. So we have a battery here. Oh no. So we have a battery and another battery, and both of them are connected this way. And then we have a resistor in here and another resistor here connected to this battery, and another resistor in here connected to this battery. So that's basically how the drawing is. It's a good idea to draw while you're reading the input anything, all of the information. So we have a 24-volt battery on the left, 3 ohm resistor next to it, and then a 2 ohm resistor with an EMF epsilon, which we don't know, and we have a 7 ohm resistor. So let me go back to the drawing. So this is 24. This is 3 ohms. This is an EMF of epsilon. And this is a 7 ohms. And it's a 2 ohm. And what else do they say? And they say that specifically there is a current of 1.8 amps running through the 7 ohm resistor. Each EMF source has negligible internal resistance. I mean, you can assume that the 3 ohm and the 2 ohms are their internal resistance, but they will be too big for these values. So we have in here a 2 ohm, okay? I'm assuming the units match up. So we have a 1.8 amp current. It has to be in this direction because both batteries are pushing the current this way. So there is no other way for it to be in the other direction. So the current has to be coming down through here. Okay, so they want to know, what's the question? It's most likely the EMF, because that's, so we need the EMF. We need epsilon. So we don't know what this value, so we need to find it basically. Okay, we have a 7 ohm and we have a 1.8 current. So the voltage drop from here to here is 7 times 1.8. So that's going to be 7 times 1.8. I think I have my calculator up and running. 7 times 1.8. So that's 12.6 voltage drop. So this is 12.6 volts. Okay? And it's actually the same voltage drop here too, between this point and this point. And it's the same voltage drop here, there too. Okay? So if I want to write Kirchhoff's rule for this loop, okay, I can do it starting from any point. I'm going to start from this point. So I'm going to find the voltage drop of 12.6 volts. It's already calculated. We don't have to write it in Ohm's law because we know it's 12.6 because it's R times I. So it's 12.6 volts. I don't know what the direction for this current is. So I'm going to take an I running through this resistor in here. Okay, which I need to find. The reason why I need that I is because ultimately if I can find this I, and I already know it's 1.8 running through here, so I can subtract the 2 and now I have the current that runs through this battery. Okay, so that's basically the plan. It's trying to find what this current is ultimately. Okay, I prime if you want to call it I prime. Okay, through this EMF. Once we find it, we know the whole drop is 12.6 volt. And there will be a current drop times this one. So the only thing that is going to be left is this voltage drop or rise. So let's write the Kirchhoff's rule for the outer loop, the one that I draw with the big arrow. So I have 12.6 through the resistor of 7 ohms plus another drop of 3 times I. And now I have to cross this resistor in a rise, actually going by 24 volts up. So I'm going to drop by negative 24. So the whole thing is equal to 0. If I solve this equation, it should give me the value of I, which should be simply equal to 24 minus 12.6 divided by 3. So that should give me the current overall that is coming from the entire circuit. So I have 24 minus 12.6 divided by 3. It's 3.8 amps. So this is 3.8 amps. 1.8 of which, so this current in here is 3.8 amps. 1.8 of which has gone through this section. So I must have 2 amps running this way, running down. In other words, the 24 volts must be higher than this epsilon for it to push the current against it. Okay? Because they are actually connected now in a sense. They are connected in series, in parallel, the negative with the negative and the positive with the positive. So they must be working against one another, and the most powerful will run the current through the weaker one. So I expect epsilon to be less than 24. Okay, I expect the EMF of this battery to be less than 24 to see this current running through it. Now I'm going to take the second loop. I'm going to take this loop now. Okay, and see how much that will give me. Okay, I'm going to drop by 12.6 again through the 7 ohms. But now I have to be careful. The current is running this way because 3.8 is coming this way, 1.8 is moving this way. So that means 2 amps is running down. So the 2 amps, I'm going against it now when I go through this side. Okay? So I'm going to be rising a potential, in other words. So I'm going to be rising by 2 times 2 amps times 2 ohms because the resistor is 2 ohms. And then I'm going to go in the same direction now as the EMF, which means I'm going to drop by negative epsilon minus epsilon. So this must be equal to 0. So this should give me 2 times 2 is 4. 12.6 minus 4 is 8.6. So the EMF is 8.6 volts. Does this make sense to you guys? Yes or no? Is this what group 3 found? Okay, if you happen to move against the current, if you are in the same direction as the current, you're dropping in voltage on a resistor. Okay. So, and since Kirchhoff's rule, the way we stated them is that it counts for the voltage drop. So you start from in the same direction as the current, so it's really a voltage drop. But when you go against the current, it's actually a negative drop. That means you're rising, okay? Because you're against it. So it's a minus negative number, which is a rise because we're counting the drops, okay? Negative drop is a rise. So let me go into the sharing the screen again to see what's going on. So I've used two loops, okay? And I've used one node actually. I didn't really explicitly state those, but they are there, okay? In the node equation here, I said the incoming current, which I needed to find, must be equal to the 1.8 plus the other number, okay? And that's how we found the 2 amps there, using the node equation there for this circuit. This node equation is the same. In other words, there is a 1.8 and a 2 amp, it turns out, and they're coming out as a 3.8 amps, okay? So these two nodes, they resolve only to one of them. And the same thing, it looks like I have 3 loops, but in actuality, I have used only 2 loops. The first loop is throughout the external thing. The only thing that is given to us in this problem is this voltage drop, because they tell us specifically that the current is 1.8 amps. So there is a voltage drop of 12.6, because 7 times 1.8 must be 12. So that's basically the voltage drop that we have. So from this outer loop, I have, doesn't matter where I started immediately after the battery. So I go, there is no voltage drop in here across. Then once I hit the resistor, that is a 12.6 drop, because I'm in the same direction as the 1.8 amp. Now, if I go this way, I labeled it as I don't know what this current is, running through the battery and this 3 ohm resistor. So 3 times I, that's another voltage drop, okay? But now, I'm coming from the negative end of the battery to the positive end of the battery, so I'm really not dropping, I'm rising by 24 volts. So what I'm saying in here, I'm dropping by negative 24. That is the same thing as saying I'm going up by 24 volts. So that gives me back to the starting point, the whole thing must be equal to 0. Since everything is known in this equation except the current I can solve for the current I, and the current I will turn out to be 24 minus 12.6 over 3, which is 3.8 amps. Now, I know the current now, which is 3.8 amps, and I know this one, which is 1.8 amps. That's what was given to me. So that leaves me with 2 amps running against this EMF. So what I say in this case is take another loop now. It doesn't matter which actually, because this voltage drop from here to here is 12.6 regardless of where I take it. So I took it this way, but I could have done it this way too, on either direction, okay? It doesn't matter, clockwise or counterclockwise. So I took this direction, which is the clockwise direction. So I started from this point, going through 12.6 drop, but now I have to be careful. The current is running down. So I cannot be dropping by 2 times 2. I'm actually rising because I'm against the current now. So I'm actually, this point in potential and this point in potential is higher by 4 volts for the current to be running down. So this point in here is 4 volts higher than this one, because 2 times 2 is 4. So I know this point in here, whatever it is more by 4 points than this point. So I'm going up by 4 volts, okay? In other words, I'm dropping by negative 4, okay? And at the same time, now I'm going against the will of the battery too. I mean, I'm against in the same direction as the battery. So I'm actually rising in potential. What I'm saying in here, since I'm tallying all the drops, this is a real drop. This is a rise by 4 volts, and this is a rise by epsilon, which turn out, if this equation is correct, to be 8.6 volts. Does this make sense to you guys? Yes? Jacob, you're the one who asked the question. Okay, good. So for us, Jacob, Okay, very good. So I hope that it's clear. If not, you really need to do more examples of this one to understand. When I stated the, I mean, sometimes Kirchhoff's rule is kind of loosely stated in different ways. You can count actually for the voltage drop, for voltage rising. So that means you have to go, if you go for the voltage rise, the increase in voltage, then across the capacitor, I mean, across the battery is going to be a rise from negative to the positive. But then if you're doing that, then there is a rise. If you are in the same direction, there is a rise of a negative 12.6 across the battery. I mean, across the resistor. So you have to be careful in here in terms of your signs, that's all, okay? Once you stick to a certain convention, which we, from day one, I said that we're gonna follow the drop in voltages. If we are really in the direction of the current, we are actually dropping, okay? That is how current flows from higher potential to lower potential. Okay, it ranges from the high to the low. So if I'm counting the drop, then that is the real drop. But if I'm going in the opposite of which, I'm actually rising in voltage. So the current for it to drop from this point to this one, I must have risen in potential. Since I'm counting just the drops, I'm going to count that as a negative drop, which means I went up in potential. And the battery, whichever way you hit it, if you hit it from top to bottom, from the positive to the negative, that's actually a drop too. Let's go back to this example and reverse the situation and see if it makes sense. So let's go back into the share the screen again and do it in the opposite direction. So what I'm going to do now, I'm going to go back to the third loop, but I'm going to change the direction to be clockwise direction. I mean, counterclockwise. We've been doing clockwise direction. So I'm going to come in here. I'm going to go counterclockwise. Now, since I'm going counterclockwise, I'm going against the current in here. You guys see that? I'm going against the current. So I'm actually rising in potential by negative 4 volts. And I'm rising in potential again by negative 8.6 volts. Okay. When I hit the 24-volt battery, I'm coming from the positive to the negative. That means I'm actually dropping by 24 volts. Okay. But now the current I that I measured to be 3.8 is actually in the opposite direction. So I'm actually rising by 3.8 times 3. Okay. So let's see if the number, it should give me 0. Okay. So I'm going to go clockwise. So I'm against the current. So it's a negative 4 volt. Negative 4 volts minus 8.6 plus 24. Remember, I'm coming from the positive side now. When I hit the battery now, the 24 volt battery, I'm coming from the top to bottom when I'm going counterclockwise. And then finally, I'm coming down through this end in here by 3 times 3.8. Okay. The potential is the current is higher this way because this potential in here is higher than this point because I'm going against the current. So I'm actually dropping by a negative number. So it's a minus 3 times 3.8. This must be 0 because I closed the loop. By the time I come back, because I started from the 4, so when I started from here, I went up by 4. I went up by 8.6. So this is a negative drop, and this is a negative drop, and this is an actual drop by 24 volts. So this is actually a drop of 24 volts, positive 24. And then in this direction, when I'm still moving counterclockwise, I'm actually going against the current. But the current now is 3.8, not the 2 amps. So it's through 3.8 times the ohm in there. So my point in here is that this numbers must be equal to 0 if I add them up. Negative 4, negative 8.6, that's negative 12.6 actually. 3 times 3.8, it should be the difference. I don't know how much 3.3. Let's multiply it. 3.8 times 3. It's 11.4. So positive 24 first, minus 11.4. This must add up to 0. And it does. If you don't believe me, just add the numbers. This is negative 11.4, which is this product in here. So that is basically, it makes sense. But I did it backward now. I did not, usually when I'm doing these things, I try to go follow one path, okay? Follow, for example, the currents dropping clockwise. But now I did it actually backward just to show that it still works. Does this make sense to you guys, everybody? Problem, what is it? I don't even, problem 60, yes? Maybe? Okay, I urge you guys to go through it again. Very good. So let's do problem 67, which we started already, but we need to finish it, okay? The first part of the question, we never tackled it, of that problem. So we really need to address it too. So let me share the screen in here. Oh, I did not share this screen. Since it's the previous tab, all I'm going to do is go back to it. So this is it. So the first question was this thing was open actually. The switch was open. Since the switch was open, at that point, the 36 drop, let me redraw this one in here. It's already a mess in there. So that's part B, okay? So we're going to come back to it. Let's do part A first. So part A, you have in here 3 ohms, 6 ohms. Since the switch is open, so I can just leave it open. I don't care about what's in between them. So this is a 6 ohm. This is a 3 ohm. And this is where they meet again. This is a 3 ohm. And this is a 6 ohm. And now the whole thing is 36 volts. It amounts to a battery, basically, when you put the ground in there, of 36 volts. Okay, the equivalent EMF is very easy to find in this case. First of all, these two are in series. They're equivalent to just 1 9 ohm. And these two guys are also in series, and they're equivalent to 9 ohm, because 6 plus 3 is 9, both ways. So the current, when it comes in here, must split itself halfway, exactly half. Because at this node in here and this node in here, so if there is a voltage drop, and the voltage drop is 36, by the way. So it's 36 equals to 9 times I on this side, I1, and it's also 9 times I2. So the 36 volt on one side, if I take this loop, if you like, okay? If you want to call it loops. If I take this loop, and I'm going clockwise, I mean counterclockwise. So from here to here, I'm actually rising in potential. So it's minus 36. Let me go back. It's minus 36, because I'm dropping by 36, by negative 36, which means I'm rising. And now I'm following the current. So I'm actually dropping, an actual drop of 9 times I1 plus 9 times I1. And at the end, I come back to the negative end of it through this loop. So I1 is equal to 36 divided by 9, and 36 divided by 9 is 4 amps. And it's the same logic, actually, for the second loop, too. If I go through this side now and come back to the starting point, again, I drop by negative 36, meaning I'm actually going from negative to positive. Well, this means I'm actually rising. And 9 times I2, it's the same number, equals to 0. So I2 must be also equal to 4 amps. I1 is equal to I2 is equal to 4 amps. Both currents must be the same. And it's very easy to understand why. Because they're the same resistance held against the same potential, so they must have the same currents running through them. I need to know the drop from here to here. The whole drop is 36, correct? I need to know this drop only. This drop is 3 times 9. I mean, 3 times 4. So this drop is 12 volts. So how much this drop from here to here? Remember, the whole drop is 36. And a drop from, let's call this point B. I think they call it B in the problem. So from where the junction is all the way to this point, it's 3 times 4 amps, or yeah, 4 amps, and that is 12 volts. So from here to here, we must have the difference, 36 minus 12, which should be 24 volts. Okay, we don't care about the lower part actually. Let's look at this voltage drop from here to here. This is actually 6 ohms times 4 amps. So it's 6 times 4, which is 24 volts. So this is point A. So that means the left in here over is actually 12 volts because the whole drop is 36 volts. So this point, we drop from 36 down to 12. So this point is 12 below the 36. And this point is 24 below the 36. So again, this question was asked by Farzad a long time ago. Faraz, I'm sorry. And that is how to find VBA. It's simply, or VAB, that's the question. I want to think that B is a higher potential because it dropped less. So in other words, okay, you have two sides of the building. You are on the top floor. You are on the top of the building. And on one side, you drop only 3 floors. On the other side, you drop 6 floors, okay? So definitely where you dropped at 3 floors is a higher level than when you dropped 6 floors, okay? And the difference is actually going to be 3 in this case, 3 minus 6. So that's basically how the logic needs to go. So I'm going to call this point in here point C, okay? So what I'm saying in here is VAB is equal to VB minus VA, that is what I'm trying to find, is equal to VB minus VC plus VC minus VA. Look at it correctly, okay? The first one is VB minus VC. This minus that. That means this drop. Since I'm against the current in here, the current is going this way, so it's actually minus 12 volts. So the first one is actually minus 12 volts. In other words, 3 times 4, okay, minus 12. But I'm going against it. And then here now, VC minus VA. VC from this point down, I'm finding this difference. It's actually in the same direction as the current. So it's going to be 6 times 4, which is a positive 24. So this is a positive 24. So minus 12 plus 24 should be a 12 volt difference. So the point A is 12 volt lower than the point B. So this is at the higher potential versus this point by 12 volts. This is before we closed the circuit. We closed the switch. So we left the switch open. So when the switch is open, this is how it looks like. It doesn't matter what you have in here. You can have whatever. But since this is open, this is how it looks like. So this point in here is 12 volt higher than the other one. I chose that point C. I could have chosen the point D in here and gotten the same answer. But it would be 24 because I'm in the same direction now. And this one I'm opposite to it is going to be minus 12. So it's going to be 4 minus 12, and the answer should be the same thing, 12 volts. Okay, so that's part A. Part B now is the one where we started in before, and we got this bunch of equations that we need to solve. They are algebraic equations. The easiest way to deal with this kind of problems is by substitution. As I said before, this equation is not needed because they want to find what the current running through the 3 ohm is, okay? So I need to use that equation I2 into wherever I have I2. And the only equation that I have I2 for it is this one. First of all, I need to simplify this. I have a 3 everywhere. So I need to get rid of this 3's everywhere. I have a 3 in here. I have a 3 in here. I have 2 3's in here. So I'm left with a 2 in here. Same thing in here. I have a 3 in here. I have a 3 in here. And I have a 2 in here. So I need to rewrite this equation neatly. So I have a 3 in here. I'm left with a 2 in here. And 36 divided by 3 is equal to, what is it, 12? So let's rewrite these equations that I'm left with. First of all, I2 is equal to I4 plus I5. I2 equals to I4 plus I5. That's one equation. And the second equation I'm looking at is, it says that I have I2 plus I4 minus I3 is equal to 0. Or I2 plus I4 is equal to I3. I2 plus I4 is equal to I3. That is the same equation. I took the negative just to the other side. And then I have I4, negative I4. So I'm going to write I5 equals to I4 plus, okay, I have an I4 and an I4 in here. I have two I4s, by the way, in here in this equation. So we need to rewrite it neatly. I have negative two I4s minus I5, and I have two I5 minus I5. So I'll have an I5, okay? So this equation simplifies a lot the problem. So let me rewrite it, okay? I have an I4 with a negative sign, and I have another. So I have a negative 2I4, and I have a plus 2I5 and negative I5. So I have a plus I5 equals to 0. So that gives me another equation that I can get rid of one of the other. So I5 is just two I4s, okay? I5 is equal to two I4s. I5 is equal to two I4s. Let's see here what we know about the last equation in here. The last equation says I2 plus 2I5 minus 12 is equal to 0. What is it? I2 plus 2I5. I2 plus 2I5 is equal to 12. Okay, now I have a bunch of equations to solve. First of all, I'm going to get rid of I2. Remember, the whole thing in here, let's see here which current we need to find. We need to find I4, by the way. That is the unknown. So we need to get rid of everything except I4 at the end of the day. So I2, using this equation, will get rid of I2 completely. Okay? So this equation now, the second equation in this bunch would read I4 plus I5 plus I4 equals to I3. So I have 2I4 plus I5. I have 2I4 plus I5 equals to I3. So this is one equation that I have left in here, okay? And then the equation that says 5 is equal to 2I4, that is still intact. We are not going to change that equation. So I5 equals to 2I4. And the last equation, it says I2 plus 2I5. Remember, I2 is, according to this equation, I4 plus I5. So this equation says then I4 plus 3I5 equals to 12. I4 plus 3I5 equals to 12, okay? It seems to me like this equation will do the trick for us. If we take I5, which is two I4s, then I will have 3 times 2, which is 6 plus that one. It's going to be 7I4. 7I4 equals to 12. Okay? That means I4 must be 12 over 7. Please check the algebra, okay? I'm not sure if this is correct. You will have to, I'm just doing it, here, and I didn't do it before to honestly to make sure. So 12 divided by 7 should be 1.71 amps. I think Faraz had probably done it before. I think he got the same correct answer, no? Yeah, okay, he did. Okay, good. So it's 1.71 amps. That is I4. Okay, basically the trick with it is if you really were lucky enough and did linear algebra, you will have a battery of methods basically of solving the system. What I did in here by substitution. You're lucky in a sense that you have equations with the proportional basically resistances. One of them is 3, the other one is 6, and the other ones are just flipped around, 6 and 3, and the middle one happened to be 3. So otherwise, in a typical probably circuit, you might end up with all kinds of complicated resistors. I mean, and this whole thing becomes a very nasty algebra, and you will end up with how many unknowns? 5 unknowns with 5 equations, and you will end up with several pages of calculations. And I'm not joking about that. I mean, unless you have access to a numerical calculator, like this software that I'm using. Actually, let me share it with you guys. It's a free software. It can do, I think, a bunch of equations at the same time. It's from Microsoft, called Microsoft Mathematics. And when you are working, I don't know if you can see it or not, but when you are working with it, one of the things that it has in here is a system of equations. Let me try to remember where it was. Was it in here? No, this is the known equations. Okay, equation solver maybe? Yeah, you can come in here and do equation solver, and you can have a system of up to 6 by 6, which is well within reach of this problem. This problem will end up being 5 by 5, okay? So this is 6 equations with 6 unknowns, and it's going to give you the solutions to it. Now, if it's fancier than this, and believe me, 6 by 6 is a big problem, okay? It's not something that is trivial to do. Most of the times, we don't end up with this many equations. Okay, most of the times we have less equations, especially if in an exam environment, you have less than that. Or if you are in an exam environment, you will have typical problems like this one, where a bunch of equations basically disappear, and you will end up with only at the end a handful, 2 or 3 at most, to deal with, and then you solve your problem. But in real life, you end up with a bunch of equations, and linear algebra will come in handy. Most of the times you can't even do it analytically. So what you end up doing in this case is you run into C++ or any kind of other program, like for example, MATLAB or Mathematica or whatever other things. If you happen to be working for a company, they may have even their own basically vendor-made software specific for them, so that you can use that software to do things like this ones. Okay. So, but most of the time you have other problems to deal with. They are not specific for linear algebra problems. But on first approximation, you might end up with something similar to what we're doing right now. Okay. So this was quite work. I mean, to get just to the answer, which is 1.71 amps. But that's basically the logic behind it. Now, I gave you already the setup for this problem. It was in a PDF file that I shared with you earlier, guys. So please go through it again and go through the steps, okay? Make sure you're comfortable with the steps, whichever method you happen to be using. If you know matrices, that's great. If not, substitution would work fine, okay? So this is in a nutshell that problem. What else in this chapter? Okay, let me look at the problems. The next one is problem 70. And what does 70 talk about? For problem 70, this is an RC circuit. For problem 70, you have a capacitor is initially uncharged, doesn't have a charge initially, okay? The switch is closed at t equal to 0. Immediately after the switch is closed, what is the current through each resistor? So we have an 8 ohm, we have a 6 ohm, we have 3 ohm, and we have a 4 microfarad capacitor, and we have a 42 volt battery. So I need you to really focus on this kind of problems, because sometimes you have a lot of details and you might skip one of them and you'll be wondering, how am I going to find the next answer? So let me share with you the screen first so that I can show you how I'm going to do that. Share. So the EMF is given 42 volts. You're not seeing the screen?
No, for question 67, did we do part C?
What's part C?
Find the equivalent resistance.
Oh, that's once you find the I's. You have to find all of the I's, by the way. You have to find I2, I3, and I4 and add them up to find the entire I. Okay, do you
Okay.
want to continue that? Okay, let's go back to that problem.
Oh, do
Okay.
we just then divide that from V?
Yes, you have to divide
Okay.
by V because this circuit is not parallel, is not in parallel, and is not in series. Because once you have the middle section connected, you can't find a way to say that they are parallel or series. So what you do in this case, you find the entire current that is being drained from the battery, I. And you know how much the EMF of the battery is, 36 volts. Divide 36 by I, and you will know the equivalent resistance of that black box, basically. What you're looking at when you have a device like this one, for example, you have a calculator in here, you have an input of power, and if you can find basically the current that is going in and coming out, you don't need to know the details of the electronics of this device, how it's connected. This is equivalent then to an effective resistor, which is the EMF, the 5.6 volt that is connected through it probably in the bottom in here, divided by the current that is taking right now, okay? That is basically what this result is. You guys understand the plan for that? So basically, once you know the EMF, which is in this case 36, was it 36 volts? I think it is. Yeah, and then you can find the I, the total I, not just the not any through the resistors, the one that is drained from the battery, the one that is coming from the battery. So what you say in this case is 36 must be equal to some R equivalent times I. In other words, you just divide 36 by that I and you'll find the R equivalent. So that's basically the logic behind it. If you want to, it should not be hard to do now. Since you found one of the currents, you can backtrack yourself. Since we found, let me go back and to share that screen in here with you guys. Share. Since we found, no, there's not this problem, this one. Since we found already I4, correct? We found I4 turn out to be 12 divided by 7 amps, okay? Now I can go back and find what I5 is. I5 is 2, this number. So it's going to be 24 divided by 7. So that's how much I5 is. I5 is 2 times I4, 2 times I4. So it's going to be 24 divided by 7 amps. So it's going to be twice this number, 3.4, I think, amps. So now we have found I5. Let's see where I5 is flowing because I need to understand where I'm at, okay? So I5 is this current, okay? And if somehow I can find, what else do I need in here? I need this I4 plus I3. Okay, we already know what I4 is. We want to know what I3 is. We want to know what the other two currents are. We want to know what I4 is because ultimately this is what I want to find. I want to find I, okay? So that's the thing with it. And I, clearly from this picture, is I5 plus these two currents, I4 plus I3. So I need to know what I3 is. And for that, let's see here. Can I find I2? No, what is I3? I3 is this current.
I3 is equal to 4I4.
Wait a minute, wait a minute, wait a minute. There is something wrong. No, not 4 anymore. Wait a minute. Oh, there is something wrong with these equations, the way I set them up. I think there is a problem with this. That is I3, that's correct. That's I3, that's, oh, I'm sorry, you're right, you're right. So you're absolutely right. So, okay. So where is the equation for I4 and I3? Somewhere.
It was the one where we found. I think it was the one where we had I2, I4, and I3, and then I2, I4, I5.
Okay, wait a minute. I2, hold on. Let me. That's when it was open. So that gives me I4. I2 is equal to I is I2 plus I3. I2 is I4 plus I5. Okay, so we know what I2 is, don't we? because we just found what I5 is and what I4 is. So we can find what I2 is. Okay? I2 is just the sum of these two currents. So we know that. But we need to know I3, I guess. That is the problem. I3. Because once we find that, we're in business. Okay? I3 is missing. So I3, which equation has I3 in it? We don't have any equation with I3.
Top one. This the I2 plus I4 minus I3 equals 0.
This one?
Yes.
Okay. So I2.
You can set that with the other equation, the I5, I4 plus I3 equals to I.
Okay, let me get things organized. So we have I4 in this equation. We have I2, which is fine. We can find it. So this will give me I3, correct? So you're right. Okay. So we have I2, and I2 is simply equals to I4 plus I5. And we're in business since we have found I4 and I5. So we're in business. So I2 then is equal to, remember, I5 is just 2 times I4. And now when I add to it another I4, so it's going to be 3 times basically 12 divided by 7. So it's going to be 36 divided by 7. So whatever that number is going to be 3. So that's I2, okay? And then the ultimate goal now is to find I3. What is the equation that we needed to use? This one. So now I have I2, which is 3 times I4, plus I4, which is 4 times I4, is equal to 2 times I3, which means that I3 is 2 times I4, which means that I3 is equal to 2 times 12 divided by 7, or 24 divided by 7. So I3 is 24 divided by 7. And now when I add them up, so 24 plus, that's 50 divided by 7, that is the entire current. So I should be 50 divided by, was it 50? Or am I wrong on this? No, it's actually more 60. Please check the numbers, okay? I'm doing things as without a calculator. So this is how many amps that I have. And now if I want to find the equivalent resistor, it should say, the equivalent resistor should say, then in this case, 36 volts divided by this current. That means divided by 60 times 7. And I'm not sure, okay? At this point, I really need to plug in things correctly and go clean, and I'm not doing it. I'm just going, the point in here is you have to solve the algebra correctly in order to find these things. But I'm just giving you an example, hopefully that, so let me see here. So what I said at the end is 60 times 7 divided by, what did I say in here? It's actually divided by 60. 36 divided by 36 divided by 7 divided by 60. 36 times 7 divided by 60. Okay, it's telling me 4.2 ohms. Okay, that's what this thing is saying. Again, please check the numbers. Okay, so it's telling me that's the answer. What did you find for that, Faraz? I'm sorry, I'm calling because I met somebody before in the past by this name. So
Yeah, I got the same answer.
yeah, 4.2 ohms. Okay, so after I divide all of these things, and I know I'm going quick with it because we have so much things to do. So please check these things. You are accountable for this thing. Check them. Okay. Okay, so let me put this thing to charging because my computer is coming down. Okay. So the problem that we were trying to discuss now is problem 70. Problem 70, basically, you have a battery. Of 42 volts. You have an 8 ohm and a 6 ohm, and you have 3 ohm in series with a capacitor. So this is not like what we did in class, okay? So you have to be careful with this thing. This is because the circuit now is not a simple RC circuit. So I'm gonna start drawing this thing. So I have a 42 volt EMF going through an 8 ohm resistor, going through 6 ohm resistor, and closing back. And now we have a resistor and a capacitor, and the whole thing is connected this way. Let me check the numbers to make sure I have them correctly. One of them is 3 ohms, and the other one is a 4 microfarads. Whenever you're dealing with these problems, leave the micro intact. Do not mess with it. Do not put the powers and all of that. Leave the micro as is, as if part of the unit. So it's 4 microfarads. 4 microfarads. And this one was a 3 ohms. Okay. And it says in here, immediately after the switch is closed. This is how the circuit looks like immediately after the switch is closed. When you close the switch, and there was a switch in here apparently, okay, this looks like it's a wire, that's it. Okay? Because the current will flow straight through. So there is no 4 microfarads immediately after you close the switch. Roughly after t greater than 0. Once the switch is closed, this is how the circuit would look like. You have 8 ohm in series with a 6 and a 3 ohm that are in parallel. So the 3 and 6 and a 3 ohms, they're equivalent to the following resistor. 6 times 3 divided by 6 plus 3. So this are 6 times 3 is 18 divided by 9. That is 2 ohms. So basically, this is how the circuit look like. This even 2 don't exist. It's like you have a 2 ohm in here. And a 2 ohm and an 8 ohm look like a 10 ohm because they're in series. So basically, the whole circuit looks like immediately after you close it, you have a battery in here of 42 volts, and you have a 10 ohm resistor. So there is a current that is drained immediately of 42 divided by 10, which is 4.2 amps. This 4.2 amps will go through the 8 ohm. So that is I through the 8 ohm is 4.2 amps. Part of it will be split through the 6 ohm, and the other part will be the 3 ohm. Now the voltage drop between here and there, I can use whichever loop law that you want, like this one, okay, to find this current. So in here, I have a drop. Let's take this immediately before the switch. So I have a drop of 8 times 4.2 plus a drop of 6 times this current, which I need to find, I through the 6 ohms, and then a rise of 42 volts. So that should give me an equation for the current through the 6 ohms. So that should give me let's start from the switch. You said 8 times 4.2 plus 6 times an I6, which I don't know what its value is, minus 42. I tend to write 24. Minus 42 equals to 0. Okay. So this gives me an equation. When I move the 42 to the other side, it's going to be a positive number. When I move this number 8 times 4.2, which should be equal to 8 times 4.2, 33.6 volts. So it's going to give me I6, which is 42 minus 33.6 divided by 6. And the current running through the 6 amps should be equal to 42 minus the 33.6. And the whole thing is divided by the 6 ohms. So that should give me 1.4 amps running through the 6 ohms. Now I have two choices. Either I subtract from the 4.2 this 1.4, and it should give me a current that is going to be there, which is what is it? 4.2 subtracting from it 1.4 should be 2.8 amps. So this resistor must have a 2.8 amps. Or I could use, again, Kirchhoff's rule for the outer loop. It should give me the same answer. So that's something that I can check right away. So I go from here, from the switch down to the 8 ohms. I know how much that drop is, 33.6. I just calculated it. So I have 33.6 volts plus another drop of 3 times the current, which I don't know, through the I3, minus 42 equals to 0, because I'm going to go back through the battery again. So this is the loop I'm taking. I'm taking this loop. I'm going around from the outer loop back to through the battery. So I'm going to drop by a negative 42. So this whole thing should give me the correct answer also for I3 being 2.8 amps. So there is twice as much current going through the weaker resistor than the bigger one. So we have answered part 1. So we found all the currents for part 1. You guys understand? So immediately after you turn it off, after you close the circuit, you close the switch, the capacitor, as if it doesn't exist at all. It will allow all the current that can run through it, and that is 2.8 amps. That's the maximum current is going to run through it. Now, after you wait, and that's probably the second part. Usually that's typical how the second part is of the question. Now, what is the final charge on the capacitor? That means you wait a long time, in which case the capacitor will block any current running through it. So at that point, this is how the circuit would look like. The resistor doesn't matter now, R3, because there is no drop in it, because there will be no current in here. So I will be 0 in here. So this is how the circuit would look like then. Because there is no current, so there is no voltage drop. So this is still 42 volts, still 8 amps. I mean, still 8 amps, still 8 ohms. And this is still 6 ohms. So there is no problem from here. It's this part in here. Since there is no current now, I'm going to write it just to wire the resistor. There is 0 drop in there. Because there is no current. This current I is equal to 0 now, after you wait a long time. So the capacitor will cancel any current running through it. So if you're asked to find the current through this resistor, you know that I is 0 after you wait for a long time. And this is still 4 microfarads. So they want to know how much charge has accumulated in here. Okay? Well, we have, again, if I apply Kirchhoff's rules, now I have a current I that is going to go through this resistor and immediately here, because I is 0 in here. So there is the same I that goes through this resistor, and this loop now should give me what that current is. So that loop should give me what that current is. So I have 42. Let's take the same scenario in here. We start immediately next to the switch. So I have an 8 times I, that's how much I'm dropping, plus 6 times I, because again, all the current itself through this node is going to go here. The current as it comes is going to go through here, because nothing will go through the other side once this is fully charged. Okay? So same current I will go through the 6 amps. Again, minus 42 is equal to 0. Of course, 8 plus 6 is 14I. 14I equals to 42. That means I is equal to 42 divided by 14, and 42 divided by 14 is 3 amps. That's 3 times 14 is 42. Okay, so I don't need a calculator for that. So now we have the current running through the 8 ohm. So if you're asked to find what that current through the 8 ohm and the 6 ohm, it's going to be the same current, and it's going to be this number. Okay, it's very simple. Okay, now how much charge now? I need to find what this voltage drop is, or I use Kirchhoff's rule for this circuit now. Let me change color. For this circuit now, I drew it in purpose counterclockwise to see how that is. So there is actually a voltage drop between here and there, which is Q over C. There is no voltage drop across the resistor because there is no current through it. There is still 3 ohm in here. but there is no current running through it. So there is no voltage drop. In other words, 3 times 0. That's how much drop is. So if you want to be explicit about it, it's 3 times 0 plus Q over C minus, because I'm going to go against the current now. The current that I just found out is being 3 ohms, 3 amps. 3 amps times 6 ohms. So minus 3 times 6 is equal to 0. By the time I come back to the same node in here, I started with this node. Okay? Excuse me. 3 times 6 is 18. This is 0. So Q must be equal to 18 volt times C, which is 4 microfarads. 4 times 18 is 80 minus 8, which is 62. No, 72. Sorry. 72 microcoulombs. That's the charge. Do you guys understand this kind of problems?
I understand how to do the problem, but I wanted to ask, like, why does the capacitor why does it function the way it does in this problem?
Okay, initially you're building charge in the capacitor. Initially there was no charge in it, correct?
Mm-hmm.
So it basically will allow, no matter how much current you're going to run through it, it's going to allow it. But after a while, it's going to build a charge in it, and it's going to basically oppose any more build-up in charges. Because once it reaches saturation, there is no more. At that point, it's going to kill the current in here. In this segment, okay? So initially, it acts as if it's a wire. That's why I didn't even bother to draw it. Okay? You just draw it at t equal to 0, immediately after the switch is on. Actually, you can think about it also in terms of the voltage across it. The voltage across it, remember, this is how the behavior for the charging cycle is. So initially, there was no charge. So the voltage across it is Q over C, which is 0. Okay? After it reaches saturation, it's going to be whatever charge it has, which is what we just found, divided by C. Okay? At that point, the current actually is going to drop. It's going to be 0 when it's fully charged. So when it's fully charged, there is no current running in where the capacitor is. So that's why there is no voltage drop in here, because there is no current there. Okay?
So is this how devices in general charge then?
I'm sorry?
So, and speaking in real application, is this how devices charge, or is that different?
They usually have a mechanism to cut off. Okay, when you build the charge, they don't usually use capacitors because they use other mechanisms to build charges in a system. But sometimes a capacitor is used to charge. For example, for the flash, you build the charge, so it takes few taus, few RCs, and then once it's fully charged, it's charged. Then at that point, wherever the capacitor is, in that section, there is no more current where the capacitor is. Now, if there is a power, let's say, for example, there was a switch in this problem. I didn't draw it right now. There is a switch, and this switch is closed. Okay, and you wait for a long time. It's closed now. There is no current through it. Let's say, for example, you open the switch right away after it's fully charged. Of course, there will be no current running through this one because the switch is open now. So where is the current going to go through? But in here, there will be a current. Now there will be a discharge cycle. Okay? Through this resistor of 3 ohms and the 6 ohms. Okay? So there would be power consumed through the 3 ohm and the 6 ohm. So this would look like a 9 ohm again, acting in this direction. Okay? But that's not part of this question. The question was, you're charging the capacitor, basically. Initially, there was no charge in it, so it acted like a wire. And then after you build the charge for a long time, and now the charge is in it, so it's going to kill whatever current running through it. But there is still a current running through this thing. As a matter of fact, we found that current to be equal to 3 amps. So there is still current drain from the battery. Initially, we were taking 4.2 amps from the battery, because part of the current was actually going toward the charging of the capacitor. And after the capacitor has fully charged, at that point, we were only draining 3 amps from the capacitor, because we still, from the battery, because we still have 2 resistors now that are draining the power from the battery. Okay? So as long as these two are working, you have no problem. And here they're draining 3. But initially you're draining more than you actually doing when at the end, because part of the power actually was going through this 3 ohm to build charge through the capacitor. The capacitor now is fully charged. It has 72 microcoulombs already in it. And that's it. That's all she wrote. She cannot take more than that. Okay. At that point, it's going to kill the current. No more current is going to run through it, meaning that there is no current also running through the 3 ohms, I'm sorry. Okay. And all the current that initially was 4.2 amps being drained from the battery, now it's only 3 amps because you still have that part of the circuit that needs to run current through it. Does this make sense to you guys?
Yes.
Okay. Everybody else too? Okay. So the next problem from this chapter, I'm hoping that you guys will review the other chapters too, okay? And if you have any questions before Wednesday, before tomorrow, actually, please ask them so that we can discuss them. Okay, so let me check what the other problem was. Problem 78, and then 81. 78. A resistor with R equals to 850 ohms. Is this 78? Am I correct on it, or I don't want to give you, yeah, 78. So a resistor R is connected to the plates of a charger. A charged capacitor with capacitance 4.62 microfarads. Just before the connection is made, the charge on the capacitor was 6.9 microcoulombs. Oh, millicoulombs, I'm sorry. I have to be careful in here. What is the energy stored in the capacitor? This should be easy because I know the capacitance and I know the charge. So let me share with you the screen. Share with you. Oops, what happened here? I am not sharing. Share this screen. Let me open a new tab for this problem, okay? So basically what we have a capacitor and a resistor. This is easy. Obviously, the current is going to flow this way if this was a positive Q and this was my negative Q. So there is a switch in here that controls when this thing is happening. Yeah, Q squared over 2C. Does everybody agree with Faraz? Yes? Since we have Q, and so we're in business. But the only thing I want to be careful with for us and everybody else is the units, okay? I want you to really pay attention to this game in here of units because sometimes it can be a nasty thing. Don't convert things. Leave them the way they are. That's basically my advice for you guys, okay? So we have, I mean, you may have to do in this case because we have a million micro, so we have to use 1,000 somewhere, that's all, okay? So the capacitor has a charge of 6.9 millicoulombs. So I'm gonna say it's 6.9 thousand microcoulombs. That's the only difference I'm going to do. From there, I'm gonna be in business, okay? That's the only advice I'm gonna have for you guys. So it says in here, 6.9 times 1,000 squared divided by 2 times. So there is a microcoulomb squared in here divided by the capacitance. The capacitance in this problem was 4.62. 4.62. Again, a microfarad. Cancel this with that, and the answer is going to be a microjoule. Okay? Because I see that there is a 10 to the power 3 squared, that's a million. And a million with a micro will cancel. So the answer is going to be in joules now. The only thing I have to do is 6.9 squared divided by 2.46. So that's the only trick with this question. So 6.9 squared divided by 2 times 4.62. It's 5.15 joules. According to my calculator, this is 5.15 joules, okay? If it were not for that 1000 in there, I would have left the answer in microjoules. Okay? I have no problem with that at all. Okay? Microjoule or a millijoule is the same thing. I mean, why would I have to put 10 to the negative 6 somewhere and probably have to bother with this? The only reason why I did it this way right now is because I have a mismatch of units. I have somewhere a micro farads and the other place is a milli coulombs. So I had to convert to one or the other. In doing so, I ended up with a million, but they have a negative 10 to the negative 6. So I cancel things around. Okay. I know in the exam and everything I give these prefixes, but honestly, I don't want you to do them. I don't want to mess with them, okay? Unless I absolutely have to. Like in this situation, it looks like it's obviously it's in there. Okay? Otherwise, I will have 10 to the power 6 microjoules and they cancel each other anyway. A million microjoules, okay? 5,150,000 microjoules, which is 5.15 joules. It's like I am so rich, I have, what is it, 100 pennies, okay? So that's the same thing as saying I have 5 million microjoules. Okay, so let's look at the second part of the question. I don't think this is it. Okay, what is the electrical power dissipated in the resistor just after the connection is made? After the connection is made, the voltage drop now is across the resistor, and the voltage drop is Q over C, and the resistor is Ri. So we need to find what the current I is, and the current I will be Q over C over R. So it's going to be Q over. Where is my notes in here? So after immediately we do it, remember the voltage drop across the capacitor is that initial charge, which is 6.9 millicoulombs, divided by the capacitance. Okay, so it's going to be 6.9 times 10 to the power 3 microcoulombs divided by 4.62 microfarads. Cancel the micro, so the answer is in volts already. 6,900 divided by 4.62 volts. Now, this is the voltage drop is going to be immediately across the resistor. And did they give us the resistance now? The resistance is 850 ohms. So the voltage is going to be times basically the current. So we need to really find what that current is. So I is going to be this voltage drop, 6.9 times 10 to the power 3 divided by 4.62 divided by 850. So this should be the actual current that is going to initially start running through the capacitor. So the current I is going to be 6,900 divided by 4.62. And I have 850 also on the denominator, 850. That should be the current of 1.757 amps. Okay, I square it and I multiply it by R. That should give me now the power. So I'm going to square this number and multiply it by 850. Since the question was the power, it's 2,624 watts. So let me share with you that screen again. So once I find this current, which turned out to be 1.575 or something, basically after you do this this division, then you're going to multiply Ri squared, and that should be the power. You square this number, you multiply it by 850, and the answer is 2,624 watts. Okay? Does this make sense? This is immediately after t equal to 0. There is all the charges still in the capacitor of 6,900 microcoulombs sitting on it, or 6.9 millicoulombs sitting on it. So there is all kinds of charge sitting on it. Since there is nothing else in the circuit, that voltage drop must be the one across the resistor. Or if you want to, you can use Ohm's law in this case. Okay, so there is not Ohm's law. the Kirchhoff's rule in this case, okay? Just follow the drop in this case. So there is a drop of Ri in this case, and there is a rise of Q over epsilon. So it's Ri minus Q over epsilon, because I'm going to come from the negative side, so I'm going to rise, is equal to 0, and solve for I in this case. But it's Q naught, okay, initially. And Q naught is still 6.9 millicoulombs. So that part in here, we insert it. So we find I. Once you find I, you use the expression that we found a long time ago for the power to being Ri squared. And since R is 850 ohms, square this number of the current and multiply it by it, and you find the answer to be. Does this answer, did anybody else do this problem and find the correct answer also, or am I, or the numbers I throw in there are not correct? I need to hear from everybody. Did anybody else also check it? Remember, this was part of your homework too. Yes? Is this what you guys found? I found for the power 2,624 watts. Or 2.6 kilowatts. Is that sounds too much, doesn't it? Yeah, but the current is big now. Yeah, so initially, yes. Makes sense. Anybody to confirm the number? Sebastian, Jacob, Bao, Daniel, Faraz, Miles, Eric? No? Nobody? Okay, it's your job really to check it, okay, because I'm just showing you how to solve these things.
Okay, yeah, I just plugged into the calculator. I got the same thing.
You got the same thing, very good. Okay, it's you really, guys, everybody else, you really need to make sure that you have to know how to do these things, okay? Because once we move past these chapters, we're not going to come back to these things, at least in this class. Hopefully, when you take electronics, you're going to delve far more in details or to circuits. But at this point, that's probably the most we're going to do in this kind of stuff. Okay, so let me continue, because I think that's not the only question that we have in this problem. So we found what is the electrical power dissipated in the resistor at the instant when the energy stored in capacitor has decreased to half the value calculated in part A. Okay, so when the charge drops by a factor of half, I think it should be half too, okay? Because remember, the charge now is following this. This is Q naught. This is the 9,600 microcoulombs, or 9.6 millicoulombs. So this is exponential of minus T over RC. This is what we found in lecture. And R is 850, and C is equal to sorry, C is equal to 4 microcoulombs, 4 microfarads, I'm sorry, in this circuit. And the question was specifically, what is the electrical power dissipated in the resistor at the instant when the energy stored in the capacitor has decreased to a factor of half? So if I find the energy in the capacitor, the energy in the capacitor later on in the future is still Q squared over 2C. Okay? And Q squared over 2C is Q naught squared over 2C times exponential of minus T over RC squared, meaning you have to multiply by a factor of 2. Now here is what the problem is. This is the rate at which the charge is dropping. I mean, the energy is dropping. This is the initial energy that we found. This is how much initial energy we found in the capacitor. of 5.15 joules. So U is 5.15 joules exponential of minus 2t over RC. The current also is dropping with a similar expression. Remember, the current now is draining a charge from the capacitor. So it's going to have I is equal to minus dq over dt. So it's going to have, so it's the same expression, except that the charge, the current I will be equal to Q naught divided by RC. That's exactly what we have used, exponential of minus T over RC. So that is the current at any later time in the future. This current initially was this current, what is it? This current, okay? 1.57 or something, or 1.75. I don't remember the exact calculation, but it was somewhere 1.757, okay, amps. Okay, so this is 1.757 amps times the same exponential over RC. That means the power, which is Ri squared, is that 2,624 watts exponential of minus 2, because I have to square the current, I have to square the exponential, minus 2 over RC. When this energy drops by a factor of half, this time is sometime in the future. It's the same time when this amount also drops by a factor of half. So in other words, the log in here to find that instant is going to be the same. So in other words, when the power or the energy in the capacitor drops from 5.15 to 2.6 or whatever that half is, 2.75 or some, whatever that 2.65, I think, then this will drop to 3,000, what is it? 1,312 watts. So when the other number drops from 5.15 to 2.65 joules. Do you guys understand why I'm saying that without doing any calculation? It's because both of them have this exponential of negative 2t in them over the same RC. So whenever time this reaches a certain ratio, the other one will reach the same ratio because of this exponential. So this exponential will make sure that I drop by a factor of half. That means this is the log of whatever that half is, which is, so this exponential of negative 2 over 2 over RC now is equal to 1/2. Okay? So that means 2 over 2 RC is equal to ln of 2. So I can find what that t is. They didn't ask us what the t is, but the exponential itself is 1/2. So if that exponential is 1/2 for the energy, it's the same 1/2 in here. So if that drops so by a factor of a third, that too would drop by a factor of a third. So without doing really any much calculations, I can argue that once the energy in the capacitor drops by a factor of half, the power consumption in the resistor also drops by a factor of half. Does this make sense? Because it's the same exponential. Because the energy is dropping by an exponential of negative 2t over RC, and the power consumption in the resistor is also dropping by the same rate, exponential of negative 2t over RC. So if that exponential happened to be 1/2, to cut the energy in the capacitor to half of what it was in the beginning, the consumption also in the power in the resistor will drop by the same factor of half. So if it was 5.15 joules in the capacitor, now it's 2.65 or whatever that ratio is. Now, since it's half of what it was, the other one also is going to drop by a factor of half. So without doing much calculation, it's going to be 1,312 joules. Watts, I'm sorry, for the power. Okay? Okay, I really urge you guys to do these things. And if you are curious trying to find when did this happen? When does this happen? 2t over RC must be equal to ln of 2. And then that's give you the time t equals to RC ln of 2 divided by 2. Okay? So that is the time in the future when this is. Remember, RC is my tau in this case. So it's going to be 2 taus divided by, I'm sorry, tau times ln of 2 divided by 2. So that's the time in the future when this is going to happen. Ln of 2 is just fraction of, it's almost 1. No, yeah, it's almost 1. It's less than 1. Divided by 2 is even less than that. So it's almost half tau, less than half tau, I should say, when this happens, when the power consumption drops by a factor of 2. I hope that clarifies anything for this problem, that you guys are going to have all the information to finish it. And it's done, actually. The answer is it drops by 1,312 joules, watts for the power. But it's the argument that you have to follow. Yes? Any questions about this problem?
Is there any way to like take like get the power from taking the derivative of work?
No, they are not the same thing. They are actually, you're in a kind of a sense you might, but don't do that. That's, one of them is happening through the capacitor, okay?
Mm-hmm.
And one of them is happening through the resistor, okay? And once you're dealing with the power and energy, these are quadratic, non-linear terms, okay? You have to be very careful when it comes to that operation, doing integrations, trying to do something. You have to go back to you have to go back to basically the fundamental definitions. If it's a linear term, maybe, okay, you can argue one way or the other. And this happened to be proportional, so you might get away with it, but don't think that way in general. Because these are once it comes to the energy, everything is out of the window. Okay, you have to go back to the fundamental definitions. For example, you guys did waves in physics 4A, didn't you?
I don't think so.
You didn't do waves?
Oh yeah, springs.
Yeah, you did waves. So, for example, in that case, the wave equation is literally linear equation, and you can do superposition of waves, 2 waves coming, colliding with one another, you get another wave, which is fine. And later on, when you take 4C, basically you're going to do optics, and you have a beam of light and another beam of light, and both of them, for example, they will have constructive and destructive interference, just similar to 4A, and you will have basically a dark spot and bright spot, and you can do all kinds of things. But when it comes to power, you have to be careful too. When it comes to energy, you have to be careful. Those are not linear anymore. You have to square things first. Once they're squared, you cannot just add because of that cross term. Because one squared plus another 1 squared is not 1 plus 1 squared. You know that because of the cross terms. 1 squared plus 1 squared is 2, but 1 plus 1 squared is not the same thing. It's 4, actually, because of the cross terms. So that's the same thing. When you're dealing with the squared in here terms, you have to be careful, okay? So it's not, and the derivative and the integrations are linear operations, by the way. So you have to be careful in here. So that's the caution. In this case, you may get away with it because you only have one resistor, one capacitor. So when it's going in here, it's going there, but not true in general. You have to be very careful with it, okay?
Okay.
The only thing that is true in this problem in terms of derivative of the capacitor, the rate at which the charge is being discharged from the capacitor is equal to the current in the resistor. I is equal to minus dq over dt because the minus is decrease. You're draining the charge initially. You're discharging the capacitor. That's the only thing that is true in terms of derivatives in here. Okay? The power consumption in the resistor is the derivative of the energy consumed in the resistor. That's true. The energy in the resistor at the end is the sum from 0 to infinity of the power in the resistor. Okay? because you have only two elements, it might argue the conservation of energy, you may get away with it, but not in general. Okay, you have two different devices. The power, the rate at which the energy is drained from that capacitor, how much it's losing energy on the same time, is related to the energy in the capacitor. Okay, and that is a different term. Okay, so you have to be very careful with these things. Device by device, true, but not when you cross devices. You have to be careful. Okay, so that's problem 78. The last one is problem 81. Problem 81. Let me see, where is problem 81 in here? Okay, problem 81. You set up a circuit as shown. It's basically an RC circuit, okay, where the capacitance is 5 microfarads at t equal to 0. You close the switch and then measure Q as a function of the current. So basically, you're keeping track of Q via the voltage, probably. The voltage divided by, to find Q is multiply the voltage by the capacitance. You find what the charge is. And your results are shown in the table. So we have 5 points in this graph, correct? We have Q and I. Graph Q as a function of I. So if I graph this function, it should be a decreasing function with the current. So let me go back into sharing the screen in here with you guys. Share again, this one in here. Open a new tab since we have a new problem. Okay. So this is the current I. This is the Q. This is my independent variable. Q is my dependent variable. Initially, there is no charge in the capacitor since we are charging it, okay? So the current in here should be some value for Q, but they didn't give us this, so they gave us some points in here. If we plot them, it looks like this. So we're going to have a Y-intercept and an X-intercept. So this is an Y-intercept, and this is an X-intercept. Okay, that's really what the graph is. It should not extend to a negative on this negative side, okay? But the points, if you plot them, they should be somewhere in here. There are 5 points, okay? So these are all my 5 points somewhere. Okay? So, and the first question is, explain why the data points, when plotted this way, fall close to a straight line. The reason why is because I have an EMF, I have a resistor, and I have a capacitor, Q, and I have an R in here. I, and I have an R and I have a C. Okay, so if I use Kirchhoff's rules, we're charging the capacitor, okay? I start from before the resistor. So I'm dropping in current, so I'm going to say Ri plus Q over C equals to the EMF. So my function Q as a function of I looks like this. Q is equal to, I'm going to move the I to the other side. I'm going to multiply by C. So it's going to be RC with a negative sign times I plus, I'm going to multiply by C, C times epsilon. This is a linear function. This is of the form Y equals to mx plus b, okay? Where the slope is, in this case, a negative number, and its amplitude, its magnitude is equal to RC, okay? As the current is increasing, if you wish, the charge is decreasing, okay? And vice versa. So you have to be very careful in here. This is a line that looks like this. As the current is 0, all the charge should be C epsilon. That is when it's fully charged, actually. At that point, there will be no current running through the capacitor. So that is when I is equal to 0. When I is at its full-fledged, when I is its maximum, that is when at that point, there is no more charge in the capacitor. So that is when it's completely, that's the starting point. So this is at t equal to 0. The current is maximum. So this is I, this is Q. The current is maximum, okay? And as time builds up, the current decreases and the charge increases, okay? So this is the line. We're actually traveling it backward, okay? And the slope is negative, indicating because of this relationship. This is basically application of that law. So the slope must be equal to RC in magnitude, in absolute value. So the absolute value of M must be RC. I know it's negative because of this relationship in here, okay? And the Y-intercept is actually C epsilon. So the Y-intercept is my actually C, the capacitance times the EMF of the battery that causes the whole thing. So that's basically how the graph needs to look like. I don't have to integrate. I don't have any exponential in here to worry about. This is not a time-dependent event. This is just the relationship between Q and I, which is a line. Okay? So let's continue with this question here. So we understand why this should be a line. Explain why the data points in the way that fall as close as possible. Find the slope. So we're going to find the slope in here. I don't know. Did anybody find the slope of this data? I probably should put it in an Excel spreadsheet or something. Let me open Excel in here. This is probably the safest bet in here. So I'm going to draw I, and I'm going to draw Q. And I'm going to leave everything the way it is, okay? I'm not going to change units or anything like that. So let me stop sharing that screen and go to the Excel file, share with you the Excel file. So this is basically, if I'm doing it as a homework or it happened to be an exam or something, this is how I would handle this kind of thing. Put it on Excel, okay? Since you have data, say, so the first values, 56 and 48 and 40. What is that? 56, 48, and 40. I still have 2 more points. 32 and 24. Q, in this case, is it's increasing as it should be. 10.1 and 19.8. 10.1, 19.8. And uh, 40 and 32. No, I'm sorry, 30.2 and 40. 30.2 and 40. And the last point in here is 49.9. So let's plot this thing. Let me get this thing out of the way in here. Let's draw, oops, not draw, insert and chart, this kind of chart, that's fine, okay. Okay. I'm gonna put it in its own chart area, okay, that's fine. So plus trend line, and I want it to be a linear trend line, okay. And let me check the option to see what the equation is. There is a function, so it's negative 1.2475, but there is a function, I think, in Excel called the slope, isn't it? Equals to slope. Oops. Okay, equals to slope again. I'm sorry. So the first one is going to be the y values. So it's this values, comma, this values. So negative 1.24, exactly like this graph is saying, okay? Negative 1.2475. So that answers that question. Do you guys see the answer to that question? You don't have to do it by math. You don't have to do simulations and things like that. You can actually use Excel for it. But if it's part of a homework, I would recommend that you use this. You append this stuff in here with your homework, showing your work. Okay. Find the slope. Use your result to calculate the resistance. Now, since we know the slope, let me stop sharing the screen and share the same stuff that we have in there. Since we know the slope, and it has to be a negative number, like I said, okay, so it cannot be positive. That's good. So the fact that we found it negative is very important. So in absolute value, it's equal to RC. So RC then is equal to 1.2475, I think. And the units now, you have to be careful with units. In my x-axis, I left everything in milliamps. And in my y-axis, I left things in microcoulombs. So this should be microcoulombs divided by milliamps. So it's going to be 10 to the negative 3 coulombs per amp. So times 10 to the negative 3 coulombs per amps, which is a second, by the way. Okay. So milliseconds, that's the answer now. So that's the correct answer. It's 10 or millisecond, if you like. We have C. We don't know what R is. Is that the question? Yeah, we need to find what R is. C already is 5 times 10 to the negative 6. So this is 5 times 10 to the negative 6. And times R is equal to 1.247 times 10 to the negative 3. Cancel this one with that one. So I'm going to have a positive 10 to the power to the power 3 when I move to the other side. So I'm left with the 10 to the negative 3 in here when I do that cancellation. So it's 1,247 divided by 5. So R is 1,247 divided by 5. And that should be, according to my calculator, 1,247.5, I think, to be more specific, divided by 5. And the answer is 250 ohms. Okay, I'm rounding it now to 250 ohms. Okay, so we found what T is, what R is, and then and the EMF. The EMF, we're going to find it from the Y-intercept. Okay, so the Y-intercept, we can go back to the equation and put in it y equal to 0. So let me stop quickly how to do this in Excel. So the equation in here, it says 79.9. When you put x equal to 0, the y-intercept is 79.9, or 80 if you like to be more approximate. But so it's 79.9. That is my y-intercept. But again, the units are that of the charge, and the charge are in microcoulombs. So it's 79.9 microcoulombs. That is the y-intercept. So in this case, I'm going to go back to my. So 79.9 is equal to the B term, and the B term is C epsilon. So C epsilon, C, remember, is 5 times 10 to the negative 6 times the epsilon is equal to 79.9 micro coulombs. That are the unit for the charge. So this is 10 to the negative 6. And the negative 6 cancels the negative 6. And the answer is 80 divided by 5. and 80 divided by 5 should be like 16 volts, correct? 17.9. I'm approximating it in here, okay? 15.98 if you really care to carry that decimal points. It's roughly 16 volts, okay? So we have found the answer based on the y-intercept should give me epsilon, and the slope should give me r. So that's basically how we answered this question. At what time t after the switch is closed is the voltage across the capacitor equal to 10 volts? Remember, the initial voltage is 16 volts, okay? The charge of the capacitor is given by the expression C epsilon times 1 minus X. So basically, we're going to go back to the lecture now and grab that expression. So Q of T is equal to C epsilon, which is the y-intercept, by the way, times 1 minus exponential of minus T over RC. And RC is the absolute value of the slope. So we're going to find this expression, and it has dropped to 10 volts. So this would be 10 equals to 16 times 1, because C times epsilon, I'm sorry. What am I talking about in here? You have to be very careful in here. The voltage across it, that's not correct what I said, I'm sorry. The voltage across the capacitor is the one that drops to that value. So voltage across the capacitor is Q over C, which is the EMF times 1 minus exponential minus T over RC. Okay? That is the voltage across the capacitor. And that is the one where the 16 volt is. So this is 10 equals to 16 times 1 minus exponential of T over the slope in absolute value. Okay? So now it's just a matter of finding what that T is using the 16, moving it around and doing the log and things like that. So 10 over 16 from one side equals to 1 minus exponential of minus T over absolute value of m, where m is the slope, which is negative 1.4. So it's 1.24, whatever that, 1.25 roughly. Okay. Move this to that side and move this to the other side. So exponential minus 2 over the absolute value of the slope is equal to 1 minus 10 over 16. 10 over 16 is common denominator is 16, so it's 6 over 10. So T then is going to be equal to the absolute value of m times the ln with a negative sign, ln of 6 over 10. Okay, and that should be a positive value, where m is that positive number. So we can do the calculation in here, and we should be able to find the correct answer. You guys understand how to manipulate this algebraic equation? It should be easy enough with the ln, and you have an exponential. Because the only trick with this problem in here is you have the expression from the lecture that we found for the charging of the capacitor. Q of T is equal to C epsilon times 1 minus exponential of T over RC. RC is the actual slope in absolute value. So that number that we found, negative 1.2457, just take it 1.24575, okay? And that should be RC itself. C epsilon is actually the y-intercept, which is 79.9 microcoulombs. But once you divide by C, it's just the EMF, which is the 16 volt that you just found. Now this is 10 volt. This is 16 equals to 1 minus T over the absolute value of the slope. Now from here, 10 over 16 equals to 1 minus the other one. Move the numbers around. The negative becomes positive when you move it to the other side. The 10 over 16 becomes negative. And the common denominator is 16. 16 minus 10 is 6. Divided by 10 is 6 over 10. And then take the log now, the natural log. So it's going to give you negative T over m equals to ln of 6 over 10 multiplied by negative m. So, and this is a positive number, by the way, because ln of a fraction is negative times the negative should be positive. And the correct answer should be, if I plug in things in the calculator, negative, it's 1.2475. I'm just going a little bit being careful in here, times ln of 6 over 10.
Wouldn't it have been 6 over 16? Because 1
Oh,
minus...
6 over 16. I'm sorry. Yes, you're absolutely right. I'm sorry. That's my mistake. So, yes, you're right. Please make that correction, okay? 2475. Sometimes when I'm talking and my mind is drifting somewhere else, I make this mistake. 6 over 16. Thank you for the correction. Okay. So it's 1.22 seconds. Okay. Oh, I'm sorry. It's a millisecond, remember? I took the slope in milliseconds, so it's 1.24 10 to the negative 3. So the answer is 1.22 millisecond. Because this number I put 1.24, but don't forget you have to multiply it by 10 negative 3 seconds. Okay? So that's the answer for that part. And what was the other question? When the voltage across the capacitor is 4 volt, what is the voltage across the resistor? That's the easiest thing in the world. Okay, when the voltage is 4 volt, remember the whole battery is 16 volt. Okay, the whole battery is 16 volt. And when the voltage across the capacitor is 4 volt, so the answer is 12 volts across the resistor. Okay, because there are only two things, and this is conservation of energy. So they didn't ask for anything in here other than this, so this should be easy. When the voltage across the capacitor has dropped to 4 volts. I'm sorry, it's dropped. It's increasing actually. It was 0, now it's going up. So it's 4 volts. What is the voltage across the resistor? The voltage now is 10 volt. No, I'm sorry, 12 volt. Okay. So this, you don't need to do an exponential. You don't need to do anything. This is just pure conservation of energy. You have 16 volt battery that you calculated already, its EMF. And they tell you now the voltage across the capacitor is 4 volts. How much it's going to be then across the resistor? 16 minus 4. Okay. If you like, you can use a loops, Kirchhoff's rule for the loop, but you only have two devices in here, 3 devices with a battery. So it doesn't matter where you start from. So you have an X amount drop across the resistor, plus 4 drop across the capacitor, minus 16 drop across the resistor because the voltage, because you're going in the opposite direction. You're actually rising by 16 equals to 0. So in this case, it's going to be minus 16 plus 4, which is minus 12. Move it to the other side. It's going to be 12 volts. Okay. Any question from the other questions? This is all of the questions from chapter 26. No questions? Okay, guys, then I see you. Keep the questions coming then until exam time. We're going to end this session then. Okay, bye.